So before we get into talking about how we're going to assess aircraft performance with a flight test, we're just going to discuss the drag and power curves in a little bit more detail, starting with this chart here, which you've seen before. We discussed this a little bit in class, but here again you can see the total drag curve, which is the solid black line at the top of this chart. So that's associated with the y-axis on the left-hand side, and the total drag curve is essentially the parasite drag and the induced drag curves summed together, right? And we saw that we could find the speed for minimum drag by either finding the minima of the total drag curve and reading down onto the x-axis, which is our airspeed, or we can find the point at which the parasite drag and the induced drag curves cross. Both of those methods give us the speed for minimum drag, V sub md. We also have on this chart the power required curve. So that's associated with the y-axis on the right hand side. And again, from that we can find the speed for minimum power. We just find the minima of that curve and read down onto the x-axis. And we saw in class, or we derived the equation that showed that the speed for minimum power was always less than the speed for minimum drag, and it turns out that it's 76% of the speed for minimum drag. So we're going to have a look at what this chart means physically to how the aircraft flies at different airspeeds, namely above the speed for minimum drag, below the speed for minimum drag, and then above and below the speed for minimum power. So let's first discuss the side of the total drag curve to the right hand side of the speed for minimum drag. So you can see here I've just drawn this, the longer of the two green arrows, so that is called the front side of the drag curve, so the right hand side of the drag curve. So we're above the speed for minimum drag. And if we're operating at speeds on this side of the drag curve, it's what's called flight path stable, because our drag on the aircraft increases with airspeed. So if we're operating at an airspeed above the speed for minimum drag, what happens is, if we're flying along and the aircraft is upset somehow by a gust or turbulence such that our speed increases, then so does the drag, right? So without touching the power, the increasing drag will then slow the aircraft back down to its original speed. So likewise, if this gust or turbulence results in a reduction in speed, then also the drag reduces too. So then this allows the aircraft to accelerate back to its original speed without the pilot touching the controls, right? So that's obviously a stable condition, because any upset results in a return to the original state. So that's good. That's where we want to be flying for flight path stability. So now let's consider the power required curve. So if we're operating at speeds above the speed for minimum power, so we're on the right hand side or the front side of the power curve, so you can see I've indicated that with the smaller of the two green arrows, right? If we're flying with an airspeed that's greater than the minimum power speed, then this is a very intuitive regime for the pilot to be flying in, because more power is required to fly faster, right? So that's intuitive. So this is where it's easier or more manageable for a pilot to be flying, because the controls for power are intuitive. To go faster, we just apply more power, right? So what we will often see for flight path stability in terms of the drag, the front side of the drag curve, is that for a holding pattern, so if we're in a hold, right, we're waiting to land, we probably want to be flying for best endurance, right? But the quoted holding speed generally in aircraft manuals is going to be higher than the minimum power power speed, right, just so that the aircraft is flying on the front side of the drag curve and that the pilot has flight path stability. So let's now take a look at what happens if we're flying on the back side of the drag curve. So now we are flight path unstable because now drag decreases with airspeed. So you take our little scenario where the aircraft is upset by a gust or by turbulence, such that the aircraft slows down. Well, then the drag is going to increase as well. So now the aircraft's going to slow down even more. The drag is going to increase, and so this condition starts to diverge, which is obviously unstable. But not only unstable, it's unsafe too, because eventually the aircraft is going to stall if the pilot doesn't intervene. So what's actually more dangerous than that is flying on the backside of the power curve, which is at speeds even lower than the backside of the drag curve, right? And now all of a sudden our intuitive operation of the aircraft, so apply more power to fly faster, goes out of the window, and now all of a sudden we need more power to fly slower, which is obviously not intuitive, but it's due to the increasing angle of attack, right? So let's say, for example, we're coming into land, but we find ourselves a bit low on the approach. So the pilot raises the nose of the aircraft to try to stretch out the glide into the runway, right? So that's not working. So the pilot adds a bit more power and raises the nose even more, and keeps doing that until you end up in a situation where you're flying pretty slowly with a lot of power on in a nose-up attitude. And this is a very, very bad situation for a pilot to be in, because now you're close to the ground in a nose-up attitude, flying slowly and at close to full power. All right, so you don't have any excess power to accelerate the aircraft out of this particular flight condition. And you can't raise the nose even more because the increase in drag will cause you to descend. And you can't lower the nose either because the decrease in lift will cause you to descend, and you're now very close to the ground anyway. So this is a very dangerous situation to be in, because you're close to having what's called a power on stall at low altitude, and that never works out well for anyone. So this is why, again, going back to quoted speeds for like the holding speed that we discussed on the previous slide, this is why our approach speed will always be on the right side of the power curve for intuitivity, if you like, of the flight controls, and also for safety. Alright, so now let's discuss the flight testing sequence for analysing the aircraft performance characteristics. So first of all, what are we aiming to do here? So first of all, we'd like to somehow quantify the aircraft performance and to determine our speeds for best range and best endurance. And then we'd also like to analyse the specific power plant characteristics of our aircraft. And we record all of that data is some information regarding the fuel flow rates and how they correspond to the airspeeds at which we gathered all of those data. So the first plot that we're gonna draw here is airspeed along the x-axis versus fuel flow rates along the y-axis. And obviously from that we can find the speed for minimum fuel flow rate, right, which is going to be our speed for best endurance. Okay, so we minimize fuel flow rate and therefore we maximize endurance, right? We maximize the amount of time we can spend in the air because we're at the speed where we're burning least fuel. Okay, so that's fairly intuitive. And then the second chart that we're going to plot, we're just going to convert our data a little bit into something called specific air range, SAR, which basically tells us the distance we can travel per unit of fuel. So we just use that little formula that's in the white box there, and therefore we can plot airspeed again along the x-axis, and this new parameter, specific air range, along the y-axis. And you can see now the curve has been inverted, so we now have this kind of like parabola shape, which we can take the maximum of to find the best range speed. So this is obviously dependent on a number of different things, which we're going to see on the next slide, but also just to remind you here, that's what's in the kind of blue cloud in the top corner of the screen here, is that these characteristics are not only dependent on the aerodynamic characteristics of the aircraft, but also on the power plant, as we discuss the different types in class. So let's go ahead and have a look at some example data for these two charts. So here's the first chart then. We've plotted fuel flow rate on the y-axis against airspeed along the x-axis, and you can see the different colored dots here on the chart correspond to data taken at different altitudes. And what we're trying to do here is characterize how the altitude at which we're flying affects the fuel flow rate and essentially the efficiency. So as you would expect, altitude does have an effect on the fuel flow rate. So you can see here Group A, which is the blue dots, was at the lowest altitude and had a higher fuel flow rate across the whole airspeed range. And groups B and C, which are the red and green dots here, were at the highest altitude, and they have the lowest fuel flow rates across the whole speed range. So that's as you would expect. And so you can see on the chart there, actually we've converted the pressure altitude using the temperature into a density altitude, just for convenience of plotting it. But essentially what we're seeing here on this chart is the slower that we fly, the less fuel we burn. So we've discussed this in terms of endurance flying, right? So if we minimize the fuel flow rate, we minimize the amount of fuel we're burning. This allows us to stay up in the air for the longest time possible, right? So think about applications like search and rescue when you're in the hold, that kind of thing. So for those types of applications then, should we fly at the slowest speed possible? So you can see here on the chart, the lowest fuel flow rate is at the minimum speed that we tested. So should we just fly at the slowest speed that we can in order to fly for best endurance? And the answer to that question is typically no, because although we are minimizing our fuel flow rate, we're flying at a speed which is very close to the stall, which is obviously dangerous. So actually what we tend to do is fly at a speed that's a little bit higher than that, and you can see because of the shape of this curve, we will only just be burning a slight bit more fuel than we would be at, say, if we were at 140 knots compared to 110 knots, we're burning just a little bit more fuel, but we're in a safer flight condition, and that puts us on the front side of the drag curve, and so we are flight path stable. And that's obviously a lot safer for flying around in these applications like search and rescue, stuff like that. So the next thing that we're going to discuss is specific air range. So again, we've used that formula to convert our fuel flow rates into specific air range, plotted that against airspeed, and you can see now we have, again, different tests at different altitude plotted on the chart. So here you can see that the lower altitudes, like Group A, the blue dots, give us the lowest specific air range, and the highest altitudes, Groups B and C, the red and green dots, give us the highest specific air range, right? So this is quite intuitive. So our specific air range increases with altitude, but generally occurs at a lower speed. and this is because our engines work more efficiently at higher altitudes, and also the air is thinner, so we have a faster equivalent airspeed at the same true airspeed, so we're essentially flying faster over the ground at higher altitudes. So the question is now, should we fly at maximum specific air range for best range? And the answer to that question is simply yes, if the sole objective of our flight operation is to fly the longest distance possible, right? So how does this apply to normal commercial operators, right? Well, the key for our passengers on our commercial flight is generally driven by perception and other related costs, rather than to get somewhere that's the furthest away possible, right? Unless we're talking about super long haul where it's only just possible to reach the destination for a given fuel load. So think about the new Qantas routes that were announced a couple of years ago, where it was like London to Melbourne non-stop, for example. So generally, as we'll see on the next slide, commercial operators don't fly at the speed for maximum specific air range. Generally, they just fly flat out as fast as possible. And you can see an example of why this is on this chart here. So if we accept just a 1% decrease in specific air range, we actually get an 8% increase in airspeed. So if we're looking to accept, or we're happy to accept even less than that, maybe 95% of specific air range, we're going to get a huge increase in equivalent airspeed. So the key here for a commercial operator is that, well, generally we should spend a little bit more on fuel, and therefore the aircraft is able to fly much faster to its destination, right? That's going to reduce our costs for crew, maintenance, and all of those associated costs, which are all based on flight hours. If we can get to our destination as quickly as possible, then we're going to reduce those associated costs. So this is why commercial operators don't generally fly at the speed for maximum specific air range. They generally just fly flat out, because they recoup the costs that they would have spent on fuel on other associated costs like maintenance and crew and all of that kind of stuff, which are all based on flight hours. So there we go, that's how we flight test for aircraft performance characteristics, and I'll see you in the next video.